No.
Hello, my name is Sean Manley, and I am with Team 5 from the LaSpace 2019 Fall Academy session. We're working on what we call Tucumber, the search for symmetry. Our objective is to look at Eros 433, a near-Earth asteroid that typically orbits between the orbit of Earth and Mars, though it does go a little beyond Mars sometimes. Eros has a mass of 6 times 10 to the 15 kilograms and a density comparable to Earth's crust. At its closest point to Earth, it orbits at 1.13 AU, where an astronomical unit is the distance between Earth and the Sun. Eros is 34 kilometers long from end to end and can be roughly described as a cylinder with a diameter of 11 kilometers. It has a rotational period of 5 hours. This means that the centripetal acceleration generated at the tip by the asteroid is not enough to overcome its small gravitational pull. Our plan with observing Eros 433 is to look at how it was formed. We hope to gain some insight in the formation of the early solar system. There's little that we actually know about how planets and larger bodies were formed. And in this picture at the bottom of the page, I've shown how Eros can be broken across its center of mass into 2 irregular shapes, almost like it was 2 smaller objects that collided together. We're hoping that by looking at the chemical composition and the crystal structure across the asteroid, we can determine if it really is 2 separate objects that came together, or if it formed those lumps through some process we don't yet understand, and grant us some insight on the formation of the early solar system. Sarah will discuss how we plan to reach that objective.
We're going to explore the chemical composition of each surface source using optics, namely utilizing both X-ray fluorescence and X-ray diffraction. The instrument we selected for this task is a chemistry and mineralogy X-ray diffraction instrument called CUMIN that was aboard the Mars Science Lab rover Curiosity. Most X-ray diffraction devices are the size of a large refrigerator and consume thousands of watts of power, but CUMIN is not much larger than a laptop and uses only 40 watts of power, making it an ideal choice for our mission. CUMIN will be housed within the asteroid lander, and the sample acquisition mechanism involves the lander's 2 16-inch arms. One arm controls the lander's controls a drill, and the other arm controls a 4-pronged claw that will collect samples that are each about the size of a baby aspirin. The sample wheel is mounted between the X-ray source and the detector and can hold multiple samples. Each sample cell is also reusable. Rotation of the sample wheel moves the sample into the path of the X-ray beam. A CCD records how the X-rays are scattered by the sample's atoms. Pictures are also taken of the samples, and the onboard computer sends the collected data back to Earth for further analysis via the lander's antenna. The lander's adjustable solar panel provides an uninterrupted power source for the lander and all of its instruments. The 3-legged hopper method will assist in impact absorption when the craft moves between each of our 3 selected sites. Michael will be telling you more about that.
The 3-legged hopper method is done through the legs, which unfurl from within the chassis. The unfurling and the hopper method, which is designed after human legs, is done in a way through the legs joints, which help with its flexibility. And since Eros has no atmosphere, the legs themselves can, as regular human legs are used, can literally hop around the asteroid into each landing site, which Gabby will discuss later. The legs also help with reducing landing impact with its flexibility, which I will discuss in the next slide. The lander, which will begin at a constant 20 meters per second, which changes to a 0.75 meters per second through thrust vectoring, and will also begin at a 20 degrees angle of descent to an 18 degrees angle of descent. This angle of descent is done to help with a thrust so that the lander has more controlled and slow landing. The landers change from 20 degrees to 18 degrees. Also helps with the accuracy to land at the landing sites with more precision, which Gabby will discuss in the next slide.
So we chose 4 landing sites to collect data from and to analyze. 2 of the landing sites are located on the furthest equatorial ends, and 2 are on the north and south vertical ends of the rotational axis. We decided which spots we were going to land at by using the JMARS program to take a look at the elevation and slope. It was very important to find areas that were easy to drill into and areas that were flat and not at a steep angle in order to minimize the chances of the lander not being able to collect data efficiently. The data collected from the landing sites will be analyzed and checked for similarities or differences. A difference in composition from one side of the asteroid to the other can indicate that the asteroid is made up of 2 masses that have collided, but if the asteroid is the same from the center to the end of the asteroid, we can infer that the asteroid was formed as one mass. The bottom landing site was chosen to take samples from a crater originated from a known external source. These samples will act as a good control group to compare a known difference from what is found throughout the rest of the asteroid. And in order to fund the mission, Jessica will talk about the budget.
To estimate the total cost of this mission, the budget has been broken into different sections for the closest estimation. Travel takes up 0.6% of our total budget. Faculty and administration margin takes up 2.6% of our budget, and personnel takes up 9.2% of the budget. The manufacturing margin takes up 12.7% of the budget, and the total margin takes up 23.1% of the budget. The manufacturing materials itself takes up 25.4% of the budget, and the largest portion, faculties and administration, takes up 26.4% of the budget. This includes the subcontracting with JPL and ASU's clean room. The total cost will be about $25.9 million. This is well within the requirement for a $45 million budget and gives a lot of wiggle room for any delays or added expenses. With that said, this project has a high chance of success, and we are looking at how this object evolved to its current form, whether it's the sum of 2 objects or formed independently. This will help us fill in knowledge about the universe forming that we still do not know. Thank you so much for listening to our presentation.